Good afternoon, everybody. My name is Joelle Aubin, and I am the chair of the Working Party on Mixing. And I'm here today with Michael Schluter, who is the chair of the Working Party of Multiphase Flow, and also Claudio Fonte, who is the secretary of the Working Party on Mixing. And we also have some other people online from EFCE. And our speakers. So today we're going to be talking about design rules versus digital twins and how far can modeling go. So I guess if you're connected here now, you have some interest in modeling, and we all know that numerical simulations are being increasingly used, more often, and for very difficult and different problems. And I guess many of us see as CFD simulations as being more and more accurate, and sometimes more accurate than things that we can measure, which is in some cases true. And they also give a lot of detailed information, often that we can't measure experimentally. And so numerical simulations are becoming used much more widely for design, and maybe better, to improve over the conventional design approaches that we might use, like rules of thumb and other things. But simulations, they give you so much information. And one of the questions is today, how easy is it to interpret this information? And are these simulations really representing the physics exactly? And for that, you need to be able to validate your simulations with experimental data. And sometimes that experimental data is not very easy to measure. So what we're going to be looking at today through 3 different presentations is we're going to be looking at the potential and the limitations of CFD simulations for different mixing processes, single phase and multi-phase. And we have 3 different speakers. Okay, so we have Georgina Wadsely from Unilever in the UK, and she's going to be talking to us about simulating transitional flows, so neither laminar nor turbulent. We're going to be listening to Cees Haringa on the simulation of mixing times and how you can actually encounter difficulties. And then we'll be listening to Jason Giacomelli from SPX Flow in the United States about multi-phase solid liquid mixing, okay, and different ways that it can be used. So before we start with the first speaker, I'm going to hand over the screen, to Michael Schluter, okay, and he'll say a couple of words. Now, just before I do so, I should just remind you that in order to ask questions to our speakers, you'll need to use the question and answer tab that you can see at the bottom of your screen. You write down your question, and then we will, as panelists, we will ask the question to the speaker, and the speaker will reply, or the speaker will directly reply to you in the answer tab. Okay, Michael, over to you.
Thank you so much for this very, very nice introduction. Yeah, and also from my side, welcome to our Spotlight talk. I'm very happy that we have the opportunity to bring here experts from industry and academia now together. Joelle, last week in France at the ICMF in Toulouse, we met and we discussed about these topic of mixing performance, and we very often use this as well, of course, as an important measure in multi-phase flows. And we've, as Joelle already mentioned, mixing is an extremely chaotic process. And therefore, the question is, what is the real mixing time? And due to experiments as well as numerical simulations, different mixing times can be achieved. What is the correct one? This is a big question. And I mean, many processes in industry. We are working closely together with pharmaceutical industry there, the mixing time is one of the most important characteristic parameters for process transfer and for process scale up and scale down. But what is the real mixing time? That is the question. And what is more reliable in the meanwhile? Is it an empirical approach? Is it numerical simulation? Can we do this by experiments? And yeah, we are very much looking forward to have the opportunity today to hear some nice presentations from industry and academia and to discuss this afterwards a little bit. Yeah, so therefore, let's see what we get from as new insights. And let's talk about this topic and let's see what we can learn. Okay, and with that, I don't want to take too much time from you, or maybe Joelle, would you like to add something?
Yes, I just have to apologize because I stepped in too early. And we have Antonio that has got some things to say to our members and participants. Sorry, Antonio.
Okay, thank you, Joelle. Good afternoon, everyone. My name is Antonio Gonçalves de Silva, and I am the Executive Vice President of the European Federation of Chemical Engineering, EFCE. I've taken on the role of Executive Vice President in January 2026, following one term as member of the Executive Board of EFCE. I am a chemical engineer, naturally, by training. I graduated from Instituto Superior Técnico, the engineering college of the University of Lisbon. I had an industrial career in the areas of project, erection, commissioning, and startup of industrial units. And in industry, I also worked in product development, customer service, logistics, quality, and business management. At the same time, I had an academic career. For more than 30 years, I was a professor of chemical engineering at the Lisbon Polytechnic. Finally, in the last 19 years, I had several positions at the Ordem dos Engenheiros of Portugal, the Engineers Professional Association, and lawful regulator of the engineering profession in this country. Two easy conclusions about me. One, I'm very old. Second, I've been very busy so far. I'm very happy and honored to be involved in the introduction of this webinar on design rules versus digital twins. How far can modeling go? And I'm looking forward to participating in it. Let me say something now about the Spotlight Talk series. This is now our 6th year of the Spotlight Talk initiative, which started in 2020 to keep together the community during the COVID pandemic. The success of the previous years convinced us to transform the Spotlight Talk into a regular feature of EFCE program. We have now one Spotlight Talk series in odd years and 2 in even years, such as 2026. This spring, 11 of our working parties and sections, namely mixing, multiphase fluid flow, membrane engineering, static electricity in industry, crystallization, drying, chemical reaction engineering, process intensification, education, thermodynamics and transport properties, and early career chemical engineers are delivering over 2 weeks 9 webinars of 3 or 4 talks focused on specific topics by leading industrial and academic experts. The series also enables attendees to sample matters in new areas, encouraging cross-fertilization of interests. The complete program is available on the EFCE website. EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 in Europe. EFCE's working parties and sections cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of EFCE's activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. Before concluding, I would like to thank all the colleagues who worked hard within the Working Parties section and wider EFCE for this initiative to happen and to be successful. In particular, many thanks to EFCE's Martin Pou in Toulouse, who did most of the conceptual, setting up, and practical activities. Merci beaucoup, Martin. I thank you for your attention, and I wish all the speakers and the attendees a fruitful and successful webinar. I would then give back the word to the chair of this event, Joelle Aubin, to start the webinar.
Thank you very much, Antonio. Okay, so I'd like to invite our first speaker, Georgina Wadsely, to give us her talk on characterization and prediction of transitional flow regime phenomena in stirred tank mixing. Over to you, Georgina.
Hello, thank you for the lovely introduction. So today I'm going to be presenting the work that I completed, or some of the work that I completed during my ND at the Centre for Formulation and Engineering at the University of Birmingham. And in this, I was sponsored by Unilever and the EPSRC, and now I am working at Unilever. Continuing my work in similar fields, extending more into modelling and simulation. So, the project context for my work. Many home and personal care products have a lot of thickeners and surfactants that help to build a multi-phase complex structure with a complex rheology and microstructure that provides the fluids, the performance that we require from them. However, as this complex microstructure builds, the rheology evolves and changes during mixing, often moving from turbulent flows towards the laminar regime and frequently operating with the transitional flow regime. However, currently, we know we can use models in CFD, computational fluid dynamics, for modeling stirred tanks and pipes in the laminar regime through direct solving of the Navier-Stokes equations, as well as with the application of many turbulence closure models in for high Reynolds number flows. And however, when you move into the transitional regime, how we can do this in a industrially viable way is not yet clear. So the only true way to simulate these transitional flows would be through direct numerical simulation, resolving all turbulence, time, and length scales, which would be highly computational, and it's not feasible in industry. So what's the next best thing? So a few things about running CFD simulations. You really need a good experimental validation. And these are some of the things that I highlighted in my literature review that came up as particular areas that could be indicative of the transitional regime. So Mercado et al. Found that the transitional regime, although typical values are given between Reynolds numbers of 10 to 10,000, some people have found, or they found, that even at Reynolds numbers as high as 300,000, fully developed turbulent flow was not yet seen in the full height of the tank. As well as looking at flows for similar Reynolds numbers within the transitional regime, they should exhibit self-similar flow hydrodynamics. And both Mercado et al. Mendoza et al. Observed that the mean velocity profiles are not self-similar and depend on viscosity and tip speed in the transitional regime. And I performed an initial pipe flow study that I won't discuss here, but this also revealed a lack of Reynolds number self-similarity of pipe flow past an orifice plate. So often the frequency of perturbations in transitional flow fluids mean some instabilities may persist longer for some fluids than others. So my aim is an investigative approach. I use particle image velocimetry as my experimental technique, as well as torque measurements and offline rheology. All the experiments and simulations I will present today were for Newtonian fluids. So not yet introducing this next level of complexity. So for different Reynolds numbers varying between 5 and 35,000 using water and glycerol. And the aims were from the torque experiments to find the power number and Reynolds number in relation when looking at the power curve, as well as observing trends based on the literature review in normalized velocity magnitude and normalized turbulence kinetic energy, looking at changing Reynolds number for constant viscosity fluids to establish regime limits, as well as looking at self-similar Reynolds numbers with different viscosity and tip speed to look at scaling and self-similarity. However, with the experiments that I did, I performed averaging over all blade positions. So I then looked at proper orthogonal decomposition, which is a technique that can be used to break down instantaneous flow fields into orthogonal modes. And this has the potential to help distinguish between true turbulence and the pseudo-turbulence that is introduced through the periodic rotations of the impeller. And then finally, looking at using all this experimental validation, experimental work to validate CFD simulations and explore existing turbulence closure models such as K-omega SST and I'm using ANSYS Fluent here. So first, my experimental flow measurement. These were the different setups that I used. So PIV and the torque on the right. I also performed all my experiments mostly at the small lab scale for 5-litre tank. But the torque I also performed for validation at the larger scale with 170 litres. So these are results from my torque measurements. Experimentally, I found that for the A320, with impeller half of the tank diameter and an off-bottom clearance of a third, and the tanks are also baffled. The power number was around 1.21, and the laminar constant was 62. So mainly looking at the flow fields, obviously there was a wide range of Reynolds numbers that I looked at. So I gathered a wide range of data, and it's how to extract what is the most important. So this is looking at constant viscosity fluid with increasing Reynolds numbers. As Reynolds number increases, this is a axial plot taken in line with the axis towards the edge of the tank, and the normalized flow fields start to collapse as Reynolds number increases, and this is indicative of a fully turbulent flow. However, when I looked at different viscosity fluids, so this is the same plot here, but now I'm looking at lots of different viscosity fluids, therefore within the same tip speed range of the impeller, the Reynolds number increases. However, the transitional regime boundaries were found to change with decreasing fluid viscosity. For example, to transition to fully turbulent flow, you need a higher Reynolds number for lower viscosity fluids. And this just shows how heterogeneous the tank can be. So I've just looked at one location in the tank, but then going to this higher Reynolds number, we're still not seeing fully turbulent flow at Reynolds numbers as high as you would expect to see. And this is the same for turbulence kinetic energy. You see a collapse of flow profiles as you increase in Reynolds numbers, yet the collapse is lower the collapse is at lower Reynolds number for higher viscosity fluids. And this shows the heterogeneity in the tank. So on the top, we have the normalized velocity magnitude, and on the bottom, we have the turbulence kinetic energy, and this is for the highest Reynolds number. And this clearly shows these plots are locations closer to the impeller, and this is as you move away from the impeller and up from the impeller. And you can see that the collapse of velocity magnitude profiles and turbulence kinetic energy profiles are very similar close towards the impeller. So if you're looking at the impeller, for example, or when you look at the power number, we saw the turbulent power number to reach a constant value at around 1000 Reynolds number. However, if you look away from the tank, the flow is actually not yet fully turbulent as you would expect. So Reynolds number independence is true only near the impeller, and this causes a level of complexity when you want to try and model that using CFD. And the second thing I wanted to look at was if you have the same Reynolds number but a different viscosity and tip speed. So each of these blocks here is for two similar Reynolds numbers. And although they appear very similar in their flow distribution, when you subtract the two from each other, you start to see that actually there are a few differences, even though being at the same Reynolds number, which is what Mercado et al. Found in previous literature. At lower Reynolds numbers in the laminar regime, there's very little difference between the two Reynolds numbers cases, which you would expect. However, some of these differences, despite looking similar in the contours, can represent up to a maximum difference of about 42% of the maximum tip speed observed. And interestingly, the areas in which the high viscosity tip speed and high tip speed or low viscosity tip speed dominate vary between these two regions, which could be indicative of the viscosity allowing or not perturbations to progress and move towards turbulence. This is the velocity magnitude, and a similar thing was shown with the turbulence kinetic energy differences. At these lower Reynolds number, the differences are very small, yet throughout the transitional regime, despite similar Reynolds numbers, the complex interplay between the viscosity and tip speed shifts the balance between the energy input and the flow resistance, leading to a slight difference in the flow patterns observed. And here the differences represent up to 33% of the typical levels of turbulence in the bulk flow. Again, this just highlights that the normalized mean velocity profiles do not exhibit Reynolds number self-similarity. But how can we get this out of CFD simulations when CFD simulations are based on the Navier-Stokes, which typically are normalized to depend only on the Reynolds number? So proper orthogonal decomposition, I'm not going to go too much into the background of how this is done, but more how this can be used. So this is a technique used to break down instantaneous flow field data into a set of orthogonal modes ranked by their energy content. And the first piece of information we can get out here is the eigenvalue spectrum. So how the kinetic energy of the fluctuating velocity field is distributed across the modes. This straight line here is the slope of the modes to minus 11/9, which relates to the inertial subrange of fully turbulent flow. So this is for a very low Reynolds number, but as you increase in Reynolds number, you would expect this energy distribution to be higher. Also, this plot only shows the 95, the modes containing 95% of the energy. So for large scale motion, we start here, and as the scale of turbulence decreases, so we have high energy, large scale motion. As you decrease down the cascade, you get to smaller and smaller scales with smaller amounts of energy. And the proper orthogonal decomposition, you can also get the phase portraits, which are the temporal coefficients of adjacent modes. And these help you to identify where you may have some coherent structures. So the turbulence kinetic energy could be due to more periodic motions of the impeller rather than true turbulence. So it's more forced turbulence. And this here shows the phase portraits of those two between the first and the second mode. The spatial coefficients identify the most dominant patterns or structures belonging to each mode. So here the first mode is most representative of the turbulence kinetic energy within the region that I have done this over. And then more here you can see the breakdown of where the rest of the energy is distributed. So you could begin to see why there may be some differences between two cases at a similar Reynolds number. You can see modes 3 and 4 here are quite different to modes 3 and 4 there, and there you get a difference in the energy distribution, which could lead to a difference in the flow patterns observed between two cases that have a similar Reynolds number, yet different viscosity and tip speed. And lastly, the temporal coefficients help to identify how dominant spatial structures evolve over time. So through fast Fourier transform, these are the fast Fourier transforms plotted against the frequency normalized by the frequency of the impeller. So we can see strong peaks here at 3 times the impeller rotation frequency, which relates to the 3 blades of the mixing of the impeller. And here you could suggest that there's strong force turbulence from the impeller. So any true turbulence is highly masked by this. There is a limitation, however. So my PIV acquisition frequency was capped at 10 Hertz just due to the abilities of the scope of the equipment available. So in this PIV data alone, we cannot see whether this also may have frequencies related to the impeller frequency. But it definitely has a strong peak closer to 0, which may be more representative of macro instabilities, which isn't visible within this one. Yet you can't fully confirm because of the Nyquist frequency is capped less than the impeller rotation frequency. And so here's the eigenvalue spectrum for all the experimental data that I took. So with decreasing viscosity in each of these and increasing Reynolds number. And one nice observation here is that in the laminar regime, the distribution of the eigenvalue spectrum is quite similar. Yet as you move into the transitional regime, we're seeing large differences in the distribution of the energy throughout the POD region. And this could be useful when trying to model or compare simulation and experimental data. And then you see when you start to reach the fully turbulent regime, the eigenvalue spectra are quite similar. So have we actually reached the fully turbulent regime? So onto the CFD validation. The model I've chosen is stress-blended eddy simulation. So why this? LES is the spatial filtering of the Navier-Stokes, which resolves large-scale turbulence up to the limit of the grid or the mesh, and models of small-scale structures less than this. This is of greater computational accuracy than the RANS model, which involves the averaging of the time or ensemble averaging of the Navier-Stokes equations, but must introduce the Reynolds stresses, which then need to be resolved with the addition of a turbulence closure model. Here it's the K-omega SST closure model. RANs work quite well close to the wall, whereas LES requires the addition of wall functions when resolving close to the wall. And here in the stirred tank, you have the impeller and the walls. So this is very important in confined flows. SPS is able to switch between the two. And for example, with this default blending function, the red represents where the model will run in RANs and where the model will run in LES. So this also showed promise in my pipe flow study as well. So how the simulations are set up. So data sampling on a fixed plane, averaging over all blade positions to get the same type of data that I got from my PIV measurements. I also looked at taking periodic sampling, so every full rotation, to try and estimate the pseudo-turbulence due to blade contributions when comparing on averaged at specific blade position and over all blade positions. But I really focused on looking at the all blade positions because this is directly comparable with the PIV data I had, and then performing transient sampling, and on this also doing proper orthogonal decomposition on my experimental data. One thing that's very important with the stress-blended eddy simulation and LES models is to ensure that the number of rotations or the number of data collected is sufficient to have a stable averaging of the velocity, magnitude, and turbulence kinetic energy. A few simple solution checks that must be performed when using SBS. So you have the wall Y plus. So this must be small enough for the Navier-Stokes for the equations to integrate straight to the wall. The cell convective courant number, this must be around 1 or less than 1 in order to receive a good estimation of flow. And then most important is the blending function. So it's proprietary to ANSYS, but the blending function works on picking up where there may be higher levels of turbulence within the flow and switches from the Gecko model to LES. However, when running some of my simulations, I found that the default blending didn't necessarily work so well, or it couldn't trigger the LES in regions where you would want it, or insufficient triggering of LES. So at high Reynolds numbers of 35,000, LES was triggered very well and covered most of the flow. At 700, the LES region was reduced, and at 300, this was reduced. So in order to compare, I also looked at running with a fixed blending distance so that I compare the Gecko model, SBS, and SBS with a fixed blending distance to see effect on the results. So for torque validation, I used the laminar model in the laminar regime, but I've also looked at all three models across different regimes. And the laminar model was validated for torque prediction in the laminar regime. The Gecko and SBS closure models were validated for impeller torque across all regimes. So the results fitted very well with the power curve. So if you're just wanting to look at the level of torque from the impeller, then that's okay. However, when looking at the torque balance between the impeller and the walls, therefore the ability for the simulation to capture and resolve the distribution of eddy dissipation from the impeller right the way through the fluid. There were both the Gecko model and the SBS model worked well at the highest Reynolds number. However, there was a clear difference in effectiveness between SBS and Gecko in the transitional regime. Gecko was not able to capture the energy dissipation with a 20% difference between the torque on the walls and the impeller. So you can use these models just for torque prediction, I think, but if you want to look at the flow captured or the energy dissipation, then SBS here is already showing an advantage. Just for a simple check, I ran some laminar steady state solutions. So my aim was to work from low Reynolds numbers and push the laminar model up to where it didn't work anymore before then looking at the turbulence closure models working from a high Reynolds number and pushing them downwards to see where they work well or where they start to break down. So as Reynolds number increases here, these are the axial flow profiles taken at these locations in the tank. We see a very good prediction of the laminar steady state model at 8 and 10. And close to the impeller, it works quite well for a Reynolds number of 25 and 50, but we start to see a breakdown of the model indicating the onset of transitional behavior. And again, as we move up and really using the laminar model where you wouldn't expect it to work, we start to see unrealistic flow fields and necessitating the use of turbulence closure models. So, like I said, now we're using the turbulence closure models and we're working down from fully turbulent flow and pushing them into the transitional regime. So for the normalized velocity magnitude profiles, we're seeing quite a good agreement between Gecko, SBS, and the PIV experimental data, with a good agreement between the flow profiles. Yet when we look at the normalized turbulence kinetic energy, the flow profiles are quite similar for SBS and PIV. However, the flow profile of Gecko predicts areas of high turbulence regions in unexpected locations, particularly above the impeller. And you can see this as it doesn't quite follow the axial and radial profiles as well. It still does an okay job, but when you look at this contour, maybe not. And then looking at the SBS model comparing the POD results from between PIV and SBS, we see quite a similar distribution of the turbulence kinetic energy between the modes containing 95% of the energy. And notable at this high Reynolds number, the slope of I to the minus 11/9, which represents the inertial subrange of turbulence, we're looking at a gradient quite similar to this. So it looks like we're in fully turbulent flow. In terms of the temporal coefficients, as I mentioned before, the PIV data is somewhat restricted by the Nyquist frequency for measurement acquisition from the PIV. So we can't see whether or not there is any peaks at harmonics of the impeller frequency, and therefore if we're seeing true macro stability instabilities or not. Yet the SBS is showing very similar distribution with these a large magnitude of low frequency peaks, which could represent macro instabilities. Moving down to a Reynolds number of 700, we start to see that compared with PIV, the SBS much closer predicts the flow loop. The Gecko predicts a very strong with higher velocity magnitudes and quite a little smaller. This is more obvious when you look at the axial and radial flow profiles. The SBS more closely predicts what we observe. However, any differences between the two experimental cases at a similar Reynolds number, all the turbulence closure models, Gecko, SBS, and SBS with the fixed blending distance, we always see self-similar results. Now looking at the turbulence kinetic energy at the same case, it's quite clear here that compared with PIV, the Gecko, the SST model greatly underpredicts the normalized turbulence kinetic energy throughout the tank. And SBS much better predicts the location and magnitude of increased turbulence kinetic energy. However, it's important to note here that despite the SBS not picking up a large region of LES, the default blending function here has enabled sufficient LES to get a comparable prediction between SBS with the default blending and SBS with the fixed blending distance. And both of these are in relatively good agreement with the experimental data, as you can see here. And again, very good agreement between the SBS eigenvalue spectrum as well as the PIV data, with a very similar distribution of the turbulence kinetic energy between modes, and a similar breakdown, a similar FFT of the temporal coefficients. And here there is a very small peak at 3 times the impeller rotation frequency. But from these, this is mode 1, from these alone, it looks like most of the turbulence we have here is not due to the pseudo turbulence of the periodic rotation of the impeller. And there is a high peak at a low normalized frequency, which could be indicative of macro instabilities. And then moving down again, here there's just one case, a Reynolds number of 300. And we start to see that the SBS model still does a generally okay job. But with the best agreement between SBS fixed blending distance and the PIV data. But when you look at the turbulence kinetic energy, there's quite a clear difference between the SBS with the fixed blending distance and the SBS with the default blending distance. As it was running such a small amount of LES, it's actually, the results are very similar to the SST model. And definitely the best agreement here in terms of turbulence kinetic energy is seen from the SBS model with fixed blending distance. So we've compared this SBS with fixed blending distance and the proper orthogonal decomposition results. And again, we see a very similar distribution of the tablet's kinetic energy between orthogonal modes when broken down. A very similar spatial distribution. And here we can compare the frequency at which we observe the spatial distribution of the tablet's kinetic energy. Now we're moving more to lower transitional regime. And here I've just chosen to compare the SBS fixed blending distance results, as we know that we're not going to receive as much LES activation or sufficient LES activation at this low Reynolds number. But it does show the promise of the SBS with fixed blending distance, even at this low transitional Reynolds number. And again, a very small turbulence kinetic energy. Although there is slightly more turbulence kinetic energy observed in the PIV data, which can be shown here by the distribution of the turbulence kinetic energy between modes, where the SBS FGBD model concentrates most of the fluctuation energy in fewer modes than observed experimentally, which may show slightly higher fluctuation, a higher level of small fluctuations in the experimental data that are not observed computationally. And lastly, we've reached all the way back down to the laminar regime, yet the SBS fixed blending distance model remains stable and consistent with the laminar model, demonstrating a robustness across regimes. Obviously, however, if the flow is known to be laminar, the laminar model should be used rather than a turbulence model, yet it shows the flexibility of the SBS with fixed blending distance to operate in different regimes, particularly the transitional regime, or where you may not know the exact regime. And again, there's a very, very small level of turbulence here in the PIV data, I think due to small fluctuations in experimental. Yes. And I think this is the last result I have. This is again comparing the proper orthogonal decomposition results with SBS FBD model concentrating most of the fluctuation energy in just 3 modes. This is the number of modes that contain 95% of the energy. And this reflects a reduced sensitivity to weak unsteadiness. However, the FFT is able to pick up these large coherent structures, which may be due or are likely due to the pseudo turbulence from the impeller. So any level of turbulence at this low Reynolds number is due to forcing pseudo turbulence from the rotating impeller. So at 3 times the impeller rotation frequency, that's equal to the blade passing frequency, and we see large peaks at 3 and 6 for both the PIV and the CFD data. So my conclusions are the power draw is validated across scales. So we have a laminar laminar constant. The power number is 1.2 for this A320 impeller. And both Gecko and SBS are validated for torque prediction across regimes, yet SBS outperforms Gecko for predicting torque balance. The transitional flows are spatially heterogeneous. Turbulence begins near the impeller, a Reynolds number of around 1,000, and does not reach fully tank-wide fully turbulent behavior even at a Reynolds number of 35,000. The viscosity and tip speed shift transitional boundaries, with high viscosity fluids reaching Reynolds independence earlier. And Reynolds number alone is not necessarily a universal scalar. Identical Reynolds number can give different distributions in turbulence kinetic energy experimentally, yet the turbulence closure models always predict self-similar flow. However, the proper orthogonal decomposition shows a shift from coherent to chaotic dynamics with mode energy spreading and suspected low frequency macro instabilities emerging in transitional or turbulent flows. The Gecko model provides sufficient solution accuracy for prediction of high Reynolds number flows with minimal computational expense, although it's not suitable for modeling transitional flows. The SBS shows a lot of promise, capturing turbulence more faithfully, and the SBS with fixed blending distance provides the most accurate regime-independent predictions, activating LES where required. And this just highlights the importance of high-quality data sets are essential for validating turbulence models in complex transitional flows. And here's some notes for future work for following on from my thesis. To start exploring alternative multi-parameter scaling approaches and move beyond Reynolds number by incorporating local shear rates, viscosity, tip speed. These are all suggestions what to look at next. Ensure to increase the temporal resolution of PIV greater with a Nyquist frequency greater than the blade rotation frequency, as this would increase the reliability or usability of the proper orthogonal decomposition. Extend studies to non-Newtonian fluids. This was all done in Newtonian fluids, and assess how complex viscosity behavior shifts the transitional regime onset, distribution, and power draw. It's also important when doing this to evaluate and compare rheology models, focusing on parameter sensitivity and avoiding overfitting, and improve confidence in effective viscosity predictions. I think the SBS FBD model does show a lot of promise in modeling transitional flows. However, this could be refined, optimizing the blending distance and exploring adaptive flow-dependent blending to balance turbulence resolution with computational cost. Also, it's important to pursue industrially viable CFD pathways, aiming for SBS level accuracy with lower computational costs. This has improved a lot throughout my PhD with the ability to leverage GPU accelerated CFD, reducing runtimes from weeks to days, and broaden the applicability towards more industrial mixing problems. So thank you very much for listening, and I'm happy to answer any questions or discuss.
Thank you very much, Georgina. Right. So we have some questions from the audience. The first question asked by Jonathan Lee is, what is the fixed blending distance as a fraction of the tank or the impeller diameter?
It's 5 millimeters blending distance that I have fixed, and the tank diameter is 19 centimeters, so it's like a small fraction, I think 1%. I don't know. My quick maths is but 5 millimeters in a 19 centimeter diameter tank.
Yeah, okay. Alain has asked, he's got two questions. The first one is on slide 28. I don't know if you...
Yeah, I can reshare.
Yeah, share. And I'll wait till you get it up and then I'll ask you the question.
Oops. Yeah, slide 28. Yeah.
Okay. So his question is, can you explain the difference between the magnitudes of the PIV and the CFD eigenvalues that are plotted in the spectrum?
So I think this, so I think it just comes from the SBS model not quite capturing as the same level of turbulence, a similar level of turbulence, I think here. But it's just the distribution across the first 8 modes. There is a slight difference. I think. And it could be looking at his second question. Maybe it's the ability for the PIV cannot quite pick up the same level as the SBS can.
Okay, so the second question, sorry, just for the
Yeah.
audience who hasn't read it, is did you compare in the turbulent flow regime, did you compare the mesh size of the CFD and the PIV filter to the Taylor microscale? And so, Georgina.
Yeah, I didn't do that directly for every case, but it's something we should consider more. So no, not in this case,
Okay.
but it's definitely something it should consider.
Okay. Okay, next question. So we have Jerry Kohler asking, thank you for an interesting talk, and he'd like to know what subgrid scale viscosity model was used in the LES simulations, and have you seen any impact of the subgrid scale model on the fidelity of the simulations?
So I think I used wall adaptive LES. Or- I didn't compare it to other other subgrid scale models. Oh, sorry,
Yeah,
what subgrid scale model? Yeah, it was Whale and WALE, Wall Adaptive LES, and I didn't compare it to any others. Sorry.
okay. Now we have Sydney Techum asking, in industry, we mostly wanted to compare and rank different mixing solutions or optimize in the design. You have well explained how we tend to make non-negligible error by considering transitional flow in tanks as turbulent. Do you think that the error we make by ignoring the transitional flow may lead to misranking between a mixing system or error in system optimization?
Okay. Yeah. Okay. Sorry, I'm just reading the question.
Yeah.
It's quite a long one. And it's really most of them how rank different. Yeah. So I think when you're looking to optimize the design, perhaps the differences is not that's compare or rank different mixing solutions, optimize design. How I'll explain. Transition lead to misranking. Yeah, I think it could potentially affect the error in optimization. Yeah. Sorry. It's quite a long one. Do you think that the error we make by ignoring transition may lead to misranking between mixing system or error? Yeah, I do think definitely. If you think you're operating in fully turbulent flow, but you're in this very chaotic regime, then if you've optimized a system based on this, I don't think you would reach the same output or desired output that you would want. Particularly, I think the next thing to look at is when you're looking at non-Newtonian fluids, the shear rates distribution will have a big impact as well. So thank you. Took me a while to I understand now.
And we have one last question. Have you done any mixing time experiments or simulations with tracer and compared the models like with the hydrodynamic flow predictions?
No, I didn't do any mixing time experiments during my PhD, so no, sorry.
Right, that's great. So thanks, Georgina. And we will now be listening to Cees Haringa, and he's going to talk to us about mixing time experiments, numerical experiments and validation. I'm not sure if he's going to be comparing different turbulence models, but we'll see what he's going to say now. So it's over to you, Cees.
All right. Yeah. Thanks a lot for the invite, and also thanks a lot, Georgina, for your wonderful talk. Very entertaining. And now we go to some more simple stuff, just turbulence without all that transitional regime complexity. But indeed, the last two questions were a perfect transition to my talk, because we'll indeed be talking a little bit about ranking systems in terms of mixing performance as well as mixing time determination. So reproducibility of large eddy simulations for mixing in stirred tank reactors. And the question that I wanted to start with is why move to large eddy simulations to begin with? Because there are definitely some articles which you can find out there that show that the Reynolds average Navier-Stokes simulations can quite adequately capture mixing behavior. For example, the paper by Coroneo et al. From 2011 shows this convincingly, I think, for a single Russian stirred tank system. And also, well, there has been some debate about whether you need a certain turbulent Smith number in order to accurately predict mixing or not. But also this article says, well, you don't have to tune anything as long as you have your mesh in order and your turbulence model selected well. Which was very nice, of course. And compared to LES, RONS does still save us a lot of time, even with GPU acceleration. However, when we looked a little bit deeper into literature and started looking beyond the single Russian system, so this was during my PhD in 2016, 2017, that we looked at this, we saw that with multi-impeller systems, Reynolds average Navier-Stokes models tend to predict mixing quite a bit less proficiently, or at least you would have to tune the turbulent Smith number in order to get adequate predictions of the mixing time. And relating it to the statement of Coroneo about turbulent viscosity, we thought, well, let's have a look into that. Apparently with one impeller, things are going well, but as soon as we expand to multiple ones, things are not going so well anymore. So probably the issue is really in between the impellers and not around them. So what we did was we set up an experiment where we used LDA, laser Doppler anemometry, to quantify velocities and turbulent kinetic energy in the region in between the two impellers, and also simulated that with different CFD approaches. I'm not going to take you through the data in detail because this is just part of the introduction, but what we saw basically was that compared to the experimental data that we got, RON simulations, and especially steady-state RON simulations with multiple reference frames, were not capable of predicting the peak in kinetic energy that was found in the midway between the two impellers, which is partly composed of true turbulence and partially of macro instabilities. So we moved on to different modeling approaches, one of them being large eddy simulations, and there we saw that, well, with the appropriate treatment of turbulence, we could predict this peak in turbulent kinetic energy in the midplane between the two impellers. And then if we look at the implications for mixing time, also there we saw that the mixing time was very strongly impacted by this behavior. If we look at the simplest situation, multiple reference frames, we saw that the mixing time was largely over-predicted, and eventually this over-prediction got worse with increasing mesh resolution, because the boundary between the compartments formed around the individual Russian impellers became sharper and sharper. If we then move to a sliding mesh RON simulation, we did capture the impact of macro instabilities on the situation, which led to a situation which was still over-predicting the experimentally determined mixing time, but didn't show the mesh resolution dependence anymore. And when we moved to large eddy simulations, we did see that we could also quantitatively predict the mixing times very well in accordance with the experiments. However, as you can see from the slide here, the computation time back then on a desktop CPU would increase a lot. Of course, we did not actually run this on a desktop CPU, but just for the comparison, we also provided those numbers. So we needed LES to accurately predict mixing time in this system at the cost of computation time. Now, as was already mentioned in the previous presentation, nowadays we can luckily benefit from GPU accelerated methods. In this case, we also ran a Lattice-Boltzmann simulation a couple of years ago of the same system, where we could reduce the computation time for the whole mixing procedure to 17 hours. And also for finite volume, you see that these methods are becoming more readily available. But this is still a single simulation. And in the end, we want to compare different cases, and we also want to know how robust our predictions are. So this is still N=1. So, okay, LES apparently has a benefit. Now, why this question of mixing time variability? This question came up during a discussion that we had to TU Hamburg last year, in a discussion with Professor Schluter, who mentioned that they reran the same simulation twice, an LES simulation, and got vastly different mixing times. What's going on here? What's the origin and the impact of this? Well, it was a situation that I did encounter before in another mixing study, but never really explicitly thought about. So we took it for granted that it happened. But of course, it is, when you think about it more closely, it is an interesting finding in the sense that you would expect numerical simulations to be repeatable, reproducible. And we saw here that rerunning the simulation twice, it was not strictly reproducible. So we wanted to know the origin and the impact. We wanted to see if this depended on the approach that we took, finite volume versus Lattice-Boltzmann, on the resolution of the case that we studied, as well as the numerical precision of the case that we studied. Why all this? I'll get into that. And of course, what you're also interested in is how does this compare with experimental variability, because also an experimental quantification of the mixing time will inevitably have some variability in it. So diving back into literature, it is not a surprise that LES is often irreproducible. There are other papers that talked about this, and the most notable one that we found was this one from 2008 from Senone et al., who explicitly considered the effect of different aspects on variability in a very simple flow system. And what they noticed was that eventually, like in direct numerical simulation, LES is sensitive to the exponential separation of trajectories. And the practical irreproducibility comes from the fact that every time we rerun a calculation, there will be small variations in how that calculation is being done. That might be in the round-off, it might be in the initial conditions, but particularly it will be in the parallelization and in the way different computations are scheduled with respect to one another. And if this order is slightly different, and also the round-off of those calculations might differ slightly, which will induce a small perturbation in the simulation. And like with DNS, that perturbation will eventually blow up. What Senone already described was that, well, LES is indeed sensitive to variability. Different sources eventually lead to the same type of behavior. And using higher precision arithmetic does delay the onset of visible differences in trajectories, but it does not suppress it completely. So here you see with different levels of precision, indeed, the number of iterations before which it becomes really noticeable is increased. What is also important to mention is that the statistical characteristics of the simulations are not impacted. So if you look at long-term averages of kinetic energy, of energy dissipation, maybe of power number in case of a stirred tank, these will all converge to the same value in the end over a long time. But the instantaneous flow fields will differ. And this will have an impact on mixing. Now, as mentioned, variability in mixing in itself is not something that's unique to LES. It also happens in mixing experiments. So this is an image from a large-scale fermentation mixing time determination by Frabel et al., where you clearly see that the mixing time determinations have substantial error bars. If you look in literature, however, there are papers that report confidence intervals on the mixing time determination. It's not the case in all mixing time quantification work. So that's already something that we would want to say. Keep in mind, there is variability in experimental mixing. Please also characterize that when you're doing your experiments. On the other hand, here we have a time trace from a conductivity probe experiment in a this is from an experiment, sorry. So we will read the 95% mixing time from this, typically from this criterion where the dimensionless conductivity is bounded. But this trace will look a little bit different every time we rerun the experiment. This variation initially has three sources to it. There will be some kind of a measurement error, which can be a probe delay, but it can also simply be other variabilities. There will be influence of the exact manifestation of turbulence in a particular experiment. And what was also mentioned in the previous presentation already, there might be macro oscillations in the system, which have some impact on the mixing time. Now, if we look in the role of macro instabilities, this was indeed something that we noted in this 2 impeller study that I showed you before. And we already saw it in the sliding mesh calculations as well. In this plane separating the circulation loops around the individual Russian impellers, you saw this kind of oscillation, which in the LDA signals we could also pick up from the autocorrelation of the signal we saw that there are indeed macroscopic variations in there, which are not strictly speaking turbulence itself. If you look in literature, there are also whole studies towards the impact of macro instabilities on mixing performance. For example, a study from Ducci and Janeskis from 2007, where they timed the injection of a tracer compared to the phase of the macro instability, and showed that by feeding your tracer in phase, you would get a much lower mixing time than if you would feed out of phase of such a vortex. So you could actually use that to improve the mixing time. Typical frequencies of these instabilities are in the order of 10 to 100 impeller revolutions, so right in the ballpark where our typical mixing times also are. So you can expect some impact from that. Okay, so this is some background as to why we wanted to do this study. Now, how did we go about it? So we had to quantify experimental mixing time first. We used a 2-impeller stir tank that happened to be available in TU Hamburg, Ryan Rautenbacher and those experiments, where we did 11 repeats with 2 conductivity probes of a tracer injection. Then we moved on to the numerical work, where we did studies in both MSTAR and Fluent. MSTAR is a commercial package that uses Lattice-Boltzmann CFD. ANSYS Fluent is finite volume, as you might know. Both now support GPU acceleration, which we leveraged within the study because otherwise it would not be tractable. And in total, we did 50 simulations in both packages, but we split between true repeats and injections, where for MSTAR, you can see we did 5 true repeats of the simulation, but we also added 10 injections in every simulation with interspacing of 1 second. So that if there would be notable macro instabilities in the system, we would definitely feed into different phases of this macro instability and also repeat that. So in hope to be able to discriminate between these effects. In Fluent, we effectively did the same, 5 repeats of the entire simulation and also with 10 interspaced injections again. Due to the way that Fluent is set up, we did not do these 10 injections literally in the same simulation, but we started from the same starting file and injected a different initial file, so it was really 50 separate simulations in that sense. There is a bit of variation between the way these things were being run, but the overall idea is the same. Well, the flow profile of this impeller it has a down-pumping impeller followed by a rush stem to pump things outward again. So, well, just for the shows, we have this nice movie of it, but let's now go into mixing. Indeed, what we clearly saw in our simulations was this effect of irreproducible mixing. So if we compare 2 runs of the exact same simulation, so it started from the exact same starting file with the exact same injection time, you do see that the profile that originates over time is quite distinct between the 2 simulations. You do see that it takes some more time for the tracer to reach the upper right corner of this slice, but there are definitely some differences in manifestation. And also, if we look then at the probe measurements, so these were virtual probes that were located at the same points as the physical conductivity probes in the real experiment, we saw that between these 2 simulation reruns with exactly the same conditions, there was a large variability in the T95 that was being recorded. 20 seconds in one case over 26 in the other. So really a substantial difference there. Then coming back to the earlier question, is there a risk of misranking assets if we do a mixing study? If you would run a single simulation and would get either of these numbers and compare it with a different asset, then yes, there might be a difference, a misranking, of course, in which apparatus actually mixes the best. So be careful with interpreting a single LES study in that sense. Well, we had more than a single study at our disposal. So we looked at the numerical or the experimental average in comparison with the numerical averages of all the 50 simulations for either package. And then what we noted was that compared to the experiment, the numerical simulations tend to over-predict mixing time, it seems, although the variability does overlap still with the experimentally noted variability. Between the 2 packages, so between Lattice-Boltzmann and between finite volume, there is actually very little difference. But if we look at the manifestation within the 10 individual injection times, it does seem visually that there is a little bit more variation between tracer injection points in case of ANSYS Fluent. This could have to do with the way that we injected things in Fluent compared to MSTAR, so there might be just an initialization aspect in that. It's something that with the current data, we could not really discriminate as whether this is really the impact of macro instabilities. So that is something that definitely needs some more work. We try to find it from the autocorrelations in the signals, similar to what we did before with our two Rushton tank, but the periodic fluctuations in the signal were definitely not as much pronounced this time. So if we look at the mixing distribution, here put in this violin plot in a little bit more detail, you do see that the overall distribution between the CFD packages is indeed quite similar, but overestimates the experimental mixing time somewhat, although the variability is rather similar. So this was the base case simulations. We also wanted to know what the impact of mesh dependency on this was and the impact of numerical precision. So let's start with mesh dependency. This is an example from MSTAR CFD. So we work with a fixed lattice where we just modify the lattice spacing. So there's no local refinement or anything like that. And you do see that from 90 million lattice points onwards, things seem to be rather mesh independent. For lower lattice counts, we do see that lower mixing times are being predicted. We don't just see that there's a misprediction from the mixing time plots themselves. Also, if we consider the power number, we see that that's actually overestimated with a high mesh or a lower mesh count or lower lattice count, I have to say, which explains why these mixing times are also faster. So there seems to be more energy in the system. In Fluent, because even with GPU acceleration, the simulations are still a little bit more time taking. We only consider two cases, 3.4 million grid cells and 1.2 million grid cells, where you do see some difference in the violin plots here. But if we look at the overall average mixing time and the variability therein, they were actually quite comparable. And also the power number between them was very comparable, despite the, I would say, for LES, rather low mesh resolution that was being applied. Then finally, the impact of numerical precision. So here we took the 90 million lattice point MSTAR simulation, which by default was run in single precision. And we also ran a double precision variant of it. And what we saw there was that the overall mixing time average didn't seem to be altered a lot. We did see that the distribution around this average seems to be a bit narrower, definitely like in line with the conclusions from Senonet. We do see somewhat of a suppression of, or somewhat of a reduction in variability, but it definitely does not suppress variability altogether. And also, if you look at the distribution, it does seem to be more in line with the bandwidth of experimental mixing times that we also observed. So the key findings, in the bitwise sense, LES simulations are indeed practically reproducible. A lot of that has to do with parallelization and the way things are being ordered in terms of computations. There are ways to fixate that, and there have also been studies that consider that. And then indeed you do see that things are bitwise reproducible, but that might get, that is typically then at the expense of additional computation time. Moving to higher precision does delay this effect somewhat, but it does not remove it. Practically, this means that when you're doing LES simulations of mixing in such a system, be careful with interpreting them, and ideally repeat runs a couple of times so that you can also quantify confidence intervals, especially if you want to compare different assets with each other, such that you're not looking at the tail end of the distribution. We did see that if you want to save time a bit, it seems to be an efficient way to do multiple injections in one CFD simulation so that you don't have to rerun the complete flow field all the time, but still you get nice proxy data from effectively multiple injection runs. The results were found to be grid independent, and also what we do see is that overall the mixing time is somewhat consistently overestimated compared to CFD simulations. Ongoing work well, we recently published this work in Computers and Chemical Engineering, so you can now find it at your disposal there. We're also still running tests with OpenFOAM. Ryan, who's running that, is hopefully going to report that very soon. As mentioned, at the moment, we could not yet untangle the impact of macro instabilities from turbulence variability. It would be nice to look further into that. Impact of turbulence model and boundary treatment are also definitely things that should be looked into. So that's not something we did at the moment. And we'd be very open to extend our study to other CFD codes. So you can actually find all the data and the geometry that went into writing the paper on our repository, download it there, and feel free to play around with it. And we're happy to hear from you what your findings are, of course. We already had the first one, which was interesting, which came from SimVantage, which reran with our geometry and did actually not find a lot of variation in their results. So we already had a call with them. It might be that there's something going on in the background that fixes the order of computations there, but at the moment, that's not something that we're sure of. So this is definitely already something we are looking into a bit more. And as mentioned, you're all invited to provide your results as well, and we'd be happy to discuss. Acknowledgements, of course, Ryan and Michael for the great collaboration with Hamburg. On my side, it was Hector and Peter that ran the simulations, and also, of course, the rest of the group. This was more or less a small sidetrack of our regular work, which is into hydrodynamics, mass transfer, and kinetics in bioreactors, reduced order modeling and hybrid modeling of bioreactors for digital twins. I just saw that question pop up in the Q&A. We definitely work on digital twins there, but the CFD simulations go into that to be able to calibrate them. And I'm also very interested in bioreactor scale up and scale down. In that light, we have a PhD position open if there's anyone in the audience that's interested in that. And if you want to have a live follow-up discussion, the ideal moment would be to come to the SBES conference in November/December this year, where I'd be happy to see you all in Delft. With that, thank you very much for your attention, and I'm eager to answer all your questions.
Yeah, thank you so much, Cees. Joelle, is it okay that I overtake the next? Okay. So thank you so much for the very nice and interesting presentation. We have a couple of questions, and I would like directly to start with Matteo Antogolini. He has two questions. The first one was, thanks for the interesting presentation. I was wondering if the scale of the tank may matter. The variability of mixing may be more pronounced in bigger size tank, commercial size 100 to 1000 liter. What do you think?
Yeah, well, my traditional answer would be if we have a geometrically similar asset and we have the same Reynolds number, it should not be, but it was just saw in the previous presentation that Reynolds number is not everything. Well, at least not if you go to transitional situations and maybe more complex rheology. From the simulations that I've done so far of tanks of different sizes, we don't see a very pronounced effect as long as we're in geometrically similar and fully turbulent cases. But definitely something that always can deserve a bit more attention, even if it was just for collecting more large-scale data, because we don't have a lot of that. The picture that I showed you before from the 2000 study from Frabel et al. Was from a 22 cubic meter reactor. And that's a very nice, but also a very rare data set. So yeah, my initial feeling would say, no, it shouldn't matter, but the proof's in the pudding. The proof of the pudding is in the eating, so yeah.
Okay. Thanks. Yeah, next question is from Alain Linné, and he mentioned the interesting work, and he's surprised to write that LES is irreproducible. So he hopes that the average velocity and kinetic energy results from LES are reproducible.
Yeah.
If the test is the tracer injected for the same position of the agitator blades?
Yeah. Yeah. So what we did is indeed when we looked at the simulations, we had this 5 repeats and then 10 injections compared to those repeats. These 10 injections were all done at a different time. So in that sense, the 10 injections might be in different positions compared to the angle of the blade at that point. However, the 5 true repeats are all from the literal same starting file with the literal same settings. The literal same starting flow field, because we also first converged the liquid phase flow field before we did the injection. So that is all from a completely equal starting point. Yes. Yeah, the effect here, what we see is really from the manifestation of the order of computations in a parallelized system. So already the work from Senonet that we built on from 2008 did do studies where they also fixed the order of calculations and ran it on a single CPU as well. And then you do not see this impact. So it really does come from numerical issues with the exact order of computations and round off therein.
Mm-hmm. Okay, thanks a lot. I guess this question is answered. Then we have a question from Céline Laubière, and she mentioned first regarding the impact of the number of lattice points. Was the ratio between the resolved and the model contribution of the turbulence solving similar in all cases?
No, so well, of course, with the repeats it was because yeah, they were all the same settings. But indeed, if we look at the different mesh resolutions, then we operated all of the simulations with the exact same operating parameters, so same RPM, etc. And the mesh resolution was changed. So there, by definition, you will get a difference in the balance between resolved and unresolved turbulence as well.
Mm-hmm. Okay, thank you. And the second part of the question from Céline Laubière is about the prediction of your expectation. So, have you tried to build a law based on the parameters, cited the function, so mixing time as a function of measurement error, turbulence, macro oscillations? Do you think something like that would be possible?
It would be helpful to be able to quantify the macro instabilities in that, which with the current setup was difficult, both experimentally and in the simulations. It was also something that, and because it worked previously from the velocity autocorrelations, we hope we could simply pick it up there again. Maybe in hindsight, we should have taken a bit more time into looking at other approaches of doing that there. So it could definitely be useful. We saw that with the previous work from Duchy that you, by injecting at the right moment compared to the instability, if you know where it is, you can leverage that. So it would definitely be worth looking into. It's not something we tried yet.
Mm-hmm. Okay, thank you. Then we have one more question from Svajdek Kalai. He asked rather a comment than a question. MStar CFD does not use all functions by default. That's why to get mesh converged solution, one has to push the resolution very high to reasonably resolve the boundary layer and get consistent results. What do you think?
Yeah. Well, my experience is that, yeah, of course, yes, you're correct that it does not use the wall function, but my experience is that we don't have to go to very extreme resolutions in order to remedy that. Of course, from a purely theoretical standpoint, it's more correct to properly model the wall and boundary layer, etc., etc. But even with relatively low mesh or lattice counts, considering the fact that we're not using any local refinement, we could get mesh-independent mixing time results, which seems to be just more reliant on the bulk flow than on the wall flow. And that's also what we see in Fluent, actually. Yeah, of course, you use wall functions, but these wall functions will not be very accurate either. But in the end, it's the bulk flow that more determines the mixing time. And that's why we also got away with a 1.2 million grid point mesh in Fluent, while if you would look at formal LES, it would be way too little to do anything.
Yeah, okay.
So from a pragmatic point of view, it works. From a purist point of view, there's definitely something to say about that. Yeah.
Okay, so it's an ongoing process
Yes.
what you have to solve here. Yeah, maybe one question that is related to our industrial colleagues to characterize the optimal feeding point for mixing in industrial scale fermenters. Do you recommend to use GPU related programs or CPU related programs?
I mean, in the end, it depends on the hardware that you have available. I mean, if you have a good CPU cluster where you can do big calculations fast enough, then use that. But that's a situation that not many of us are in, especially in industry, I think. The benefit of working on GPU is that you can get good results with rather modest investments. A lot of these simulations that we do are run on gaming computers. We don't need to even go to real scientific GPUs, even though, of course, it helps a bit. But so with a modest investment, you can do a lot with GPU-based software.
Okay.
Of course, not all physics are available in CPU-based solvers yet. So that might be a limitation if you're looking at very specific, multiphase flow problems, for example. The state is not as mature yet.
Yeah, this is directly related to another question from Maria Zetnitokova. She asked if you plan also this kind of simulations in multiphase flow system in arrayed systems. Do you think?
Yeah, that would definitely be interesting. At the moment, their computation limitations are a lot more challenging. Also, you typically work with Lagrangian multiphase in M-star. You work with Eulerian multiphase typically in Fluid. So that has some impacts, of course, on how you model the physics, which all comes into play as well. Depending on the exact conditions of the flow, bubble size distributions come in, what forces exactly to include. So the nice thing about working with single phases, of course, that there's a lot less inherent variability in the parameter selection that you have.
Yeah. So more
and even there, you have different turbulence models or subgrid models, which we did not go into yet.
Yes. Maybe we need another spotlight talk for this topic. There's a lot.
And another career, yeah.
Yes, that's right. Okay, in respect of time, there are still some questions, but maybe that you can answer the questions during the next talk, Cees. Yeah, that would be fine.
I'd be happy to.
And and with that, maybe we can continue with the next presentation. Afterwards, we will run out of time. And the next presentation comes from Jason Giacomelli from SPX Flow in the United States. So thank you so much being awake, Jason. So we go to the US and looking forward to your presentation. The screen is yours.
Thank you. Can you see it?
Yes, we can see it.
Okay, all right, good, fantastic. All right, well, good afternoon. It's not that early here. I do have to work today, so yeah. Okay, so let's talk about some multiphase and multiscale modeling of nuclear waste simulants and stirred vessels. And I wrote an industrial approach because it's a bit pragmatic, practical. These projects can't last 4 years. We're on a tight timeline usually, and on an even tighter budget. So I thought this was a great topic. We did this about 4 years ago for the Department of Energy, and the gentlemen we worked for were nice enough to let us present this outward. And this is actually the first opportunity we get to talk about this. And there's probably 2 hours of talk really on this project that I could go into. So we're going to do a pretty abridged, quick one here. So this one will focus on, given the webinar topic, comparing and validating a complex CFD model against a complex experiment. And then obviously the numerical tool limitations are a big feature of these things. And then furthermore, the experiments that we're conducting here are quite challenging as well. And so our validation data is also going to be imperfect, further confounding comparisons. So won't be quite so easy as comparing blend times with CFD models or velocity profiles. We're going to get a little bit more interesting. So let's talk a quick intro on nuclear waste processing 101. And then I'll give an overview of the motivating project because I think the story is pretty interesting. There's a lot of history behind this stuff, and I find it quite fascinating myself. And then we'll do a quick preview of the CFD modeling approach because that's important and interesting. And then we'll try and wrap up with some, comparing our model to our experimental data and a couple reflections at the end. Okay, so what is nuclear waste? It's a mess. It can be a mess of many different things. It depends on how you produce it. And the best part is the storage tanks that fill up with this stuff are the culmination of decades and different processes, changing processes. You don't know what's in the tank. That's the fun part about it. It could be a mixture of neutralized waste from isotope production, It could be shredded metal from hot equipment, because when a piece of equipment operates in hot service, it's basically it has to be disposed of as well. So you put it through a giant shredder, and then it goes into the tank as well. And so now you've got all kinds of things in the tank. And why do we care? Well, we need to know, when we're disposing of this waste and treating it, where are the hot particles? Because some are hotter than others, more radioactive that is. And if hot waste gathers in one spot, when you immobilize it in, say, a grout or a vitrification process, if you have too many hot particles in one spot, you start a little, it gets really, really hot, and then it goes critical, and then you basically will burrow through your containment system and breach your containment cell. And so that is the utmost issue of nuclear waste processing, is when you immobilize it, is it uniform and understood and homogeneous? So a lot of the challenges here determine if basically how uniform the waste is, and can you keep it uniform when you immobilize it? And you need to be able to measure a lot of important things of those from a mixing standpoint, as concentration, density, and particle size distribution. And importantly, when you're trying to make these measurements, how are bulk properties affected by these low concentrations of important materials? Because they may have a high density, but they may have a low concentration, and you don't necessarily know what's going to come out of the tank at any given time. And so if you get a sample, say 50 milliliters, what is the probability that I'm going to find my little chunk of uranium that is hot? And certain sampling methods, you may miss it altogether. And a lot of these nuclear waste simulants are designed to test whether you can find these particles or not. All right, so the motivating project here, this is it's Oak Ridge, Tennessee. That is one of the national labs in the States. They make medical waste, medical isotopes and different things. They have a lot of reactors on site. There's a lot of history there from the Manhattan Project. So there's these 6 tanks in the Mountain Valley storage area. They're 50,000 gallons each. Forgive me for that volume and not SI. And there's kind of 3 phases to this. And basically you have your storage vessels, and then something called a pulse jet mixer. Some of you may, in the mixing industry, may be familiar with what a pulse jet mixer is. It's basically a turkey baster. It's imperfect in itself in terms of suspension. It's very transient in terms of temporal, like how it suspends. These kind of suspend the material, and then it's extracted and pumped over into the second stage here. And this is called basically the slurry mixing and characterization system. And that's where our company comes in. We were commissioned to kind of develop the agitators for the slurry mixing characterization tanks, the SMCT for short. We love our acronyms. And once it's in these SMCT tanks, basically it collects about 10 charges over the course of an extraction period, and then it would mix these, and it needs to get homogeneous, and it circulates it in a MMI loop, measurement instrumentation loop. And this loop has a bunch of different measurement things to characterize radioactivity, concentration. It also has a method for taking samples offline and doing further characterization. But the idea is that you produce a homogeneous mixture such that when you sample this mixture, you get representative samples, and you can understand what's in this vessel, and then you can program your grout recipe. In this case, this goes to the 3rd section here, which then mixes the waste with a grout, and then it becomes immobilized in a cask or some kind of storage vessel. That is then trucked off for storage. Yeah. Okay, so, well, we can't actually play with real nuclear waste. That's dangerous. So there's a lot of work and studies that go into developing simulants, which are then used to test all these pieces of equipment and discover how mature your technology is in terms of handling this stuff. So here you have an image of some waste. There's 17 different ingredients here that you have to combine to make your sludge simulant. And the densities vary. So obviously uranium is, 18 kilograms per cubic meter roughly. And so depending on how you want to represent the component of uranium in the actual storage, you may use something less or less dense, whatever the density of the salt is that the uranium is being, that is. You have clays, you have steel fragments here. This is stainless steel grit, about 2000 micron. And then here's some information on what the simulant looks like. So there's some dissolved solids, sodium nitrate, the various mass fractions here. What I want to note here is that the density of the liquid phase versus the density of the slurry. So if you're just running this around and trying to measure the density to establish if it's uniform, you won't really notice the difference between 1240 and 1156 in the measurement necessarily. So do you know if it's homogeneous or not based on density? Density, obviously, is basically my point here, is not a good measure. So you need to know where the solids are. You need other methods of characterizing the concentration. As you can see, when it's in the SMCT, it's designed to dilute the mixture so that the mixture in the system is about 3 to 4 volume%. So it's dilute. And so that's a kind of a key feature here that we use to our advantage when we develop the CFD model. Also, for later on, we noticed that the particle size is somewhat proportional to the mean density. So if we were going to extract particle size distribution, we might be able to tie particle size distribution to the various components of different densities. So that's a useful feature later on when we're attempting to validate this, or the model anyways. And there's a lot of experiments to go into, right? So our task basically is to develop and prove out an agitator capable of suspending and homogenizing nuclear waste simulants. Primarily, this is a physical experimentation project. We develop in small scale because it's flexible and cost effective. And then it has to be proved at 1-to-1 scale. There is no room for failure. This has to be shown to work at full scale. So they're gonna test. They did test at full scale regardless with the simulant. But the simulants that were used represent kind of a bounding or the corner. What's the worst case, the best case, the different combination of simulants that you might have. And so the question from the customer was, what happens if something else comes to the tank and it's outside of our anticipated constraints? Or what if we want to change the mixture? Can we use CFD to do a numerical version of the simulant and avoid having to retest this in full scale? Because it's quite costly. This project is very expensive. And so part of our scope was basically not only doing the reduced scale testing, but was also developing and validating or attempting to validate a CFD model that we could do, use to explore these other questions. Okay, so let's talk about what the SMCT's purpose was and what we needed to prove in the experiments. Basically, we have two modes: the characterization phase, where basically the vessel is closed, it's been filled, it needs to produce a homogeneous mixture that's circulated through the loop. And we need to confirm and prove that the agitator can produce a homogeneous vessel such that the loop is seeing a homogeneous slurry and that it's measuring a representative slurry. The second, and so that would basically look like, basically you have a full batch, and then we would take measurements between about 10 and 90% of the liquid height. And we like to choose on the upstream side of the baffle where the flow profile is the most less chaotic, I guess to say. Like, we are most likely sure that the flow is going in a certain direction, though it is turbulent and chaotic. And what we're trying to do is achieve isokinetic sampling conditions to the best of our ability so that these samples are representative. The second motive is homogeneous discharge. We then have to discharge this slurry into the next in a bunch of different stages. And so we need to make sure that whatever leaves the vessel is representative of what we just characterized. So if we don't send, so we characterize and it's got this concentration uranium and we send something that's not that concentration uranium, then that is not necessarily, that's not okay. So we basically have to show how much of the volume can be discharged homogeneously. And then we always need criteria. So we, as an agitator vendor in our experience, we kind of apply basically what we think we can do. And so basically between 10 and 90% of the vessel height, we expect it to be plus or minus 10% of the mean would be kind of our hopeful objective, what we think we can do. And then if we also look at particle size criteria, because we can measure particle size distribution for each of these samples, and we don't know, that's not a measurement that many customers ask for, and it really depends on the width of the distribution. So we kind of put a wide tolerance on that originally, and we were curious what would come out of the experiments, because you have to understand these experiments were laborious and a lot of work to take, to validate a sample going through these tubes and then taking it all the way to a particle size distribution. So it's quite challenging. All right, so just gave you an idea of what this experimental, we're going to bypass going into detail on the experiments. I can spend 40 minutes talking about these on its own, but just to give you an appreciation, here's our mixer. We have sampling ports on the side of the vessel. We can connect those to a peristaltic pump, which we circulate and extract samples from. Then we also have this loop that is a simulated measurement instrumentation loop. And that goes through a Coriolis meter because the customer was hoping to be able to use a Coriolis meter to measure the density and use that for homogeneity. And we weren't very optimistic about that, and that led to us actually modeling that to some degree. So you can see it's elaborate setup, and we have multiple impellers, and I can speak to that in more detail later. But yeah, okay. So let's look at what this looks like. Some nuclear waste. I think these videos are playing. Great. So this is what mixing of nuclear waste simulant looks like. Material can vary. So it makes it a very challenging thing to measure. So we would take replicates, we would sample for a certain duration, we would spread out the sampling period to try and capture the most representative samples possible. Okay, all right, let's move on. Right. Change slides, please. Go on. It's not gonna let me do it. There we go. All right, let's talk about the modeling approach then. All right, so obviously you can see how complex the experiments were. Let's see how complex we can make the CFD model, but also keep it practical. So we're using basically M star. So you just heard about M star. We're using large eddy simulation. And we're using this version would be circa 5 years ago, basically, when we did these models. You'll see these lines here. Those are called output lines. We basically extracted the velocity profile along the vessel so that we could attempt to use that to help tune our isokinetic sampling velocity. So we would change our sampling pump to make sure we were as close to isokinetic conditions as possible whenever you're sampling. Okay, so fluid model is large eddy simulation. We, at the time, used Smagorinsky. In hindsight, we might, I don't know if the ILES, implicit large eddy simulation, was available at the time, but since then, we've been using ILES most explicitly for these highly turbulent cases. Basic setting for Smagorinsky constant. We basically used well, I'll talk about it in a minute, but the bulk slurry, we gave bulk slurry properties. So for particles less than 60 micron, we called those part of the liquid phase or flow followers, and we measured the viscosity and density of that, and we set that to the model's bulk. Some other information here, I think what's useful is we had high resolution. We had GPUs at our disposal, so we had 400 lattice across the tank diameter, so pretty resolved, 93 million cells. Yeah, that's all that matters. Okay, so let's talk about the solids, because this is where it gets interesting, right? How do we handle these things? Well, basically, keep in mind, we have to measure this in the lab, and measuring fine particles using laser diffraction is easy, but taking samples for laser diffraction particle size measurement is quite challenging. We end up having to use wet sieve analysis, and you can't really effectively wet sieve below about 75 microns. It is miserable. So we scalped the PSD, and we said everything less than 60 microns, maybe this is a big assumption, is a flow follower, at least at the energy inputs that we're using. And what we're interested in is the large particles, because those have all the density, and those have all the size, and those are going to be the most challenging. So we devoted our computational resources to tracking the particles of importance. And what we did is we broke the distribution by particle size and by density. So we categorized them into light, medium, heavy, and dense. And so there's your kind of windows of density, and you can kind of see the distributions of each of those distributions here and how they got scalped. So we did not model the actual concentration. We basically, because it's dilute, we said it's a dilute assumption, and we'll just get the particle size distribution as accurate as possible. And we're not going to hit the concentration because we can't model that many particles. So we limited it out and just said, oh, we'll use 1 million particles. That's no different than 2 million or 3 million particles, but we're never going to hit trillions of particles. So this is the big assumption we're going to make here, and we're just going to hope that dilute is dilute, and it's not a big deal. Yeah. So that's our solid phase. We used Lagrangian particles. Third law, basically, they had density. They didn't collide. They didn't see a lot of the impellers, but they were contained within the vessel line. So speaking next to the validation strategy, questions are, what can we measure? So we can measure agitator power and torque and speed very, very easily. That's our lab is set up to do that trivially. And then we have cases like we can measure just suspended speed. So obviously, if we're going to design an agitator, we can calculate a just suspended speed, but this is nuclear waste, so we have to measure it. We need to validate and determine what this agitator is going to do. So we measured just suspended speed. That's a visual thing. Then we had to measure homogeneity. And so we basically measured along the vessel height, concentration, particle size, as I mentioned before, and we used different methods, standardized methods to do that. And like I said before, we basically scalped the PSD at 60 micron. And so we're hoping to use or make the link that in, because we can't separate the particles once we take a sample. But based on the density class, we have an idea of what the particle size is. And so we can use particle size as a second measure of understanding homogeneity. And the best part about the CFD is we can actually find those particles numerically because we put them in there and we know where they are. So that adds a little extra usefulness to the CFD. Now, so the CFD model, definitely we can output power. We can output concentration versus height, and we can output PSD versus height, but we can also output density versus height. So we have a little bit of extra data that we don't really have in the experiment. So that's how we're going to kind of compare things in that order. And so calculating local concentration in our model. And so it's important to consider that we have to gather analogous data. So we understand how we get those samples experimentally, but now we have to make sure that however we collect the data in the CFD model is analogous or as close as possible. So what we did is we kind of binned the tank up. And so this is kind of my crude drawing of a volumetric histogram, for lack of a better word. There's your baffle. This is the area where we're effectively sampling from. So this diagram's kind of to show you where we extracted with the sampling ports in this region that we kind of characterized. Our sample port is located in that area. So we basically binned this off and we binned the whole vessel up. But you could do a volumetric histogram and output concentration versus axis, radial position, axial position, and azimuthal position as well. Yeah. Okay, so let's jump into the interesting stuff. Okay, so power draw. Up here is a trace of brake power draw from the model and from the experiments for a couple of cases here. The top case is the uniform speed, which we determined was 230 RPM. The bottom set of data is the just suspended speed, which we determined was 190 RPM. And you could say, like, looks pretty good. This is both temporal data, so we have temporally resolved data because it's large eddy simulations, and it looks good. I mean, qualitatively looks nice. When we boil that down into an average, we can plot for each of these cases the experimentally determined power number. So this is the lumped power number of the whole set of 1, 2, 3, 4, 5 impellers. That's its lumped power number. We do the same thing for the large eddy simulation, and we're within 4 to 7%. And that translates to 4 to 7 or 8% for brake power. Not bad. And this last two set here, so if you remember, we have to do things in full scale. We also ran these models at full scale as well. And just to kind of what we did at the time, because we didn't have full scale measurements when we did this part, we just kind of compared power numbers between the small scale and large scale. And so we got 0.6 for the small scale, 0.59 for the large. That's pretty good agreement between scales. And so we kind of considered from a power consumption perspective, we're pretty well validated. Okay, let's look at just suspended speed. So just suspended doesn't necessarily mean that your slurry is uniform. Sometimes it can be, but not always. And the ability for the model to predict inhomogeneity is just as important as predicting whether it's homogeneous. So I like to use CFD and I like to use these cases as test modes or failure modes. And so we ran the model both, and even though the customer doesn't care about just suspended, they want uniform. We used the just suspended speed as kind of an indicator that our model is registering different concentrations of particles at different locations depending on speed. So here's some images of NJS, and you can see our gray stuff is our heaviest particle, biggest particle. That was basically driving the just suspended speed measurement. And then here's that analogous density class of particles. So these particles, they're red here because they're shown by velocity, but these represent our dense stainless steel grit. And we can see that they're kind of collecting in a similar region, which is encouraging. Okay, so what about when we look at uniformity? So this is a front view of this similar simulations. And on the left is our NJS. So you can see our particles that we mentioned before are found on the bottom in the knuckle, near the knuckle radius, kind of the last point of suspension. And then we increase the speed to 230, we see that these are more uniformly distributed. So we have less particles collecting at the last point of suspension. And so from this, we were thinking qualitatively, hey, this looks pretty good. Our model is registering maybe adequate multiphase behavior, and we can be okay with this. So let's move on to concentration. So now the green triangles are the data from experiments. So there's 3 or 4 replicates, so we have some error bars there. The error bars on the CFD data, which is the black line, that comes from just the variability of concentration versus time, which we can output for those volumetric histograms. So I felt that was a kind of an idea of the fluctuating concentration in that volume, and it made sense to kind of use that as our width of measurement or error, I guess. And this plot is kind of, so on your x-axis is normalized concentration, so C over C bar. A line drawn at 1 means you have a perfectly homogeneous system, so that's what we're idealizing as where we want to be. And then the y-axis is basically normalized axial vessel height. And so you can see that, the green triangles look pretty homogeneous at NJS, but they are kind of leaning towards, there's more stuff towards the bottom of the tank when it's to the right of 1. And if we increase the speed to uniformity, we get some interesting behavior. This point here looks like an outlier. And like I said, I could talk experimentally for a long time. This was actually a measure of it kind of unmixing a little bit when it got a little too intense. Those particles really stratified within the eddies and made sampling. It may have invalidated isokinetic conditions in certain sampling ports. But then the CFD model seems to have kind of followed the same behavior. So that was interesting. Yeah, but it's hard to tell the difference between these two plots. So what you can do is you can boil these points into one number, basically the relative standard deviation. Brings us to this plot. So on the bottom here, so RSD 1 minus this number is homogeneity, is percent homogeneity. So the lower this number, the higher the homogeneity. So our experiments, you can see that we kind of demixed, but in all cases, based on concentration, we were better than 95% homogeneous, which is pretty good, unexpected. On the other hand, the CFD model showed around 90% homogeneous, and we did see an increase in homogeneity with increasing speed. So in this particular case, the experiment shows higher degree of homogeneity than the CFD does, and that's interesting, right? Not sure I can really explain a lot more about that at this point, but this is what we kind of found at this time. All right, so let's look at particle size. So we're going to look a little closer now and see if we can't figure some stuff out. So this plot's going to get complicated. It's going to be a 4-blocker. So we'll first start with the experiment at the model scale or lab scale. And so it's the similar idea for the plot, except that we've normalized based on the particle size distribution. So if familiar with cumulative passing distribution, so D50, 50% of the particles are less than this size. So we basically plotted the D50, D10, D80, D90, D95, D98 for each port, each sample. And so it's basically kind of telling you how the distribution is moving. So you can look for different classes of particles and where they are. And you can see that it's hard to get the particles to the top of the tank. That's kind of what this leftward shift looks like, but still better than 90%. And then there's this big spike here around one of the impellers. We think this is where we lost isokinetic sampling a little bit. It's kind of strange. But other than that, it's pretty homogeneous. We'll go with that. Pretty. Looks okay. So then we actually have full-scale data for this comparison because they ran the full-scale tests a couple years ago, and so we have some of this data. Now, they had a lot more trouble getting isokinetic conditions and getting samples out of a tank that's 4.2 meters in diameter and 6 meters tall. So they had some challenges, but generally speaking, they didn't do half bad. They're able to kind of prove that they're within, say, plus or minus 15%, give or take, of their uniformity. Interesting stuff happening at this one level of about 30%. So maybe that's kind of a corroboration between scales. Tough to say. Okay, so experiments, pretty messy data, let's say, very wide, a lot less confident than or decisive as the concentration only data. So then we look at the CFD at the model scale. And oh, wow, you can just look at this plot and you say, hey, this looks really uniform and homogeneous. We get a lot of very interesting and similar agreement at the top of the vessel, which is interesting. But there's a lot tighter. The PSD is much tighter at the rest of the ports. And perhaps, we don't see the same artifact that we saw in the sampling issue because we don't have the same sampling issue in the CFD. The particles are there or not, regardless of whether I can use isokinetic sampling to get them or not. So CFD modeling is not subjected to the same experimental challenges that the experiments are. So this looks pretty positive. It's saying we can do a pretty homogeneous system here. And then we look at the full-scale version of that same model, and it's very similar as well. A little bit more variability, fair, but generally a very similar trend. An interesting little spike around here. But generally plus or minus 10%, we're hitting the 90% homogeneous condition, which is not bad with respect to particle size. But then again, in CFD, we can track every single particle, and we know where every single particle is. All right, so let's boil those numbers down into the same axial relative standard deviation plot as I showed before. And in this case, we have the experimental data at the top and the CFD data at the bottom. So we've flip-flopped here. So the difference is now we're saying the experiment is not is around, say, 90% homogeneous, and the CFD is predicting a much more higher degree of homogeneity. So we've kind of flip-flop predictions when we look at particle size. And you can see there's a little bit more variability. This line at the top here, oopsies, this is the full-scale run. So just want to stress how difficult getting samples from that size of tank is really. And you can see our lab scale data is also, it's not bad, but it's better than full scale because we had a lot more control. But yeah, so yeah, it's pretty good, I'd say. Okay, so we'll start wrapping things up here with some learning. So the experimental data for validating such a complicated model is very challenging to collect. And we took so many measures to get the best quality samples as possible. And then, taking that from a sample to a particle size distribution, there's a lot of steps that you can lose particles, make errors. It's challenging using a wet sieve as well. We had to wet sieve everything because you can't it's slurry, so you have to wet sieve it. That's a challenge. The full scale, they even had, how do you pull a wall sample out of a 6-meter tall tank? You need someone on a scaffold. No, you use piping and instrumentation to try and draw that sample out and bring it somewhere. It's even more challenging to get that type of data. Now the CFD model on the other hand has quite a few limitations, right? We can't model the exact concentration. We're limited on some of the particle-particle interactions based on, at the time, the software. So we did the best we could. We took as pragmatic approach as possible. We scalped the PSD, and we represented a bulk fluid with fines versus, separated particles. But the positive is we know exactly where all the particles are, which is helpful. So if you're really trying to do some statistics and you trust the CFDs predicting those multiphase concentration distributions well, then you might be able to use the CFD from that perspective to at least track those large particles a little bit more confidently or add confidence. And then just getting analogous data between the two systems, that we took a while thinking that through. How do we pull from the CFD a similar concentration, the same particle size distribution, and so that we had the same data as extracted in this closely the same methods, as best we could do. So, my kind of look at it is, yeah, we can get trivial, single phase behaviors trivial like power consumption. That's easy, right? Concentration, the experiment shows a better homogeneity than CFD. Interesting. By PSD, the CFD is showing a higher homogeneity than experiment. And I think that's because getting a particle size distribution is the most challenging measurement to get from this system. And so we lost a lot of experimental. We lost error there, or we gained experimental error doing that. And then some final thoughts here. So generally, it's good agreement. The model says it's homogeneous. The experiment says it's as homogeneous as we can get it. Is this a useful digital twin? Depends who you're asking and who is using it and what purpose they're using it for. We're confident we're producing 90% homogeneity between the experiments and the CFD and the full scale testing. So that's what the system will do. It might do better, but we can't prove it. Like we can't measure it any better than what we were able to do. So you can't say if it's 95 or, 98. The measurement techniques are limited on our precision. Models are getting better. It might be interesting to rerun the simulation with some more advanced, DEM particles, but we're still going to be limited on total number of particles. And so concentration, we're not, you could try a parcel model. That could be interesting. I'm not sure it's really going to change the results that much. And for critical processes, experimentation is still required. Like if it's a nuclear waste processing, you're still doing the experiments. That's not going to go away. The cost of being wrong is too great. So yeah, that's I think all I got to say on this. So thank you for your attention, and I'm happy to entertain any questions.
Yeah, thank you so much, Jason, for the very nice presentation. Very interesting to go into these two-phase system. And any questions back? Maybe I would like to directly address one question. It looks a little bit like the strongest deviations appear close to the stirrer, so on the height of the three stirrers. Can you confirm that? And do you have any idea what might be the reason for the
Well, it's really about where you're getting the best agreement for isokinetic conditions. Now, you saw there was many stirrers, there's many impellers. What we kind of attribute the major challenge was those gray particles. They were a significant concentration, and they could swing the measurement of density and particle size significantly if you found them. And you could watch them on the side of the tank. Well, I hope that was clear in the video that you could see them centrifuging inside of the larger scale eddies.
Mm-hmm.
Now, our sample ports were about 6 millimeters in diameter. So if the eddy is 30 millimeters in diameter and you're trying to draw from that turbulent structure that's there for a certain instant in time, there's some temporal aspects, there's the local chaos caused by the impeller. I mean, there's a whole lot of stuff happening there, and it looked like in some of the data that we could detect that effect. So yes, I think all the stirrers are a result of it. I think all of the variability in the data is all attributed to basically those large chaotic structures and the ability for us to draw material from.
Mm-hmm. Okay, so
it's hard to say if the CFD is showing the exact same thing because the plots are difficult to kind of compare side by side to that level of detail.
Mm-hmm. Okay, thank you. There is one more question from Aline Linné. He asked how to statistically represent the heterogeneity of the particle size, shape, and density in simulations, and how to define the initial state. So probably you are calculating spherical particles, monodispersed spherical particles, right? Or
well, we used the particle size distributions that I showed earlier, but we did represent them as spherical particles. In actuality, they're all the various materials that were made up in the simulant were mostly granular. I think the most irregular size were the stainless steel grit because of how they're manufactured. They're made from a crushing and process, so they're kind of angular, but not necessarily very. They're still pretty cubic, but just sharp edges. The initial state, the particles just we dose them in the large eddy simulation in a bunch of pucks or like cylinders that set them at the bottom of the vessel, and then they at time zero the model initializes, and then they're suspended from the bottom of the vessel, more or less. Very more or less similar to the experiment. I'm not sure if I answered that question.
Okay. Good, thank you. Yeah, and one more question from Maria Zetnikova on slide 21. She missed how did you obtain the axial distribution of particles of different sizes experimentally? How about the
yes.
particle density axial distribution? Yeah.
Okay, so the particles different sizes. Basically, we isokinetic sampling to extract a volume of sample from the side of the tank port. For concentration, those samples are about 50 milliliters each. There'll be 3 replicates. for the particle size distribution, because of that temporal aspect I mentioned, we found that we would actually collect 5 to 600 milliliters over the course of 2 minutes. So we figured that meant that sampling port was drawing from an average condition more. And once you had that cup of slurry, that was then charged to a wet sieve stack. So basically, we set up some sieve trays. I think they were 3-inch diameter sieve trays that covered the particle size distribution greater than 60 micron. And then we would flush that and we would do a wet sieve, and then those trays were put in the oven. So there's an ASTM wet sieve procedure that you can follow, and that's basically what we followed to do that.
Okay, thank you. According to this comparison to a pharmaceutical process in pharmaceutical industry with segregation and homogenization, this competition between both processes. So Maria mentioned that it might be interesting to study your system for this kind of effect.
Yeah, agreed. And I guess that's a purpose that you could utilize the CFD model for, because we can, and I didn't think I had enough time, so I left the density plots out, but we couldn't measure the density effect in the experiments, but we could pull it out of the CFD, and there was a resolved difference versus height. But you could look at how segregated those particles are within those turbulent structures. I mean, it's very visually evident in the experiments that those large particles get centrifuged out to the large certain scale eddies. But yeah, I know about the pharmaceutical mixing of just solid particles and segregation is quite a challenge in general. But yeah, so I don't know what else really to say on that, but it's interesting, and I think the model could be used to kind of look more closely at that for sure.
Some more work necessary, probably. Okay. Good. Yeah. Thank you so much. These have been the questions so far. I don't know, Claudio, wanted you to add something?
Yeah, you had your hand up.
You raised your hand.
Can ask a question. So I think that great talk, by the way, Jason. I think that this is the perfect example of a good use of a digital twin, because I don't think anyone will really want to get close to the kind of stuff that you are mixing in those vessels. But I'm just trying to understand from an industrial perspective, how do you make decisions out of these models? So we already showed that sometimes they work really well, sometimes they have some things that don't work as well. How do you make decisions out of that?
I mean, in this particular case, there's a fair bit of exploratory work that goes with nuclear stuff, with waste processing. It's like, what can you achieve? And then the scientists at the national labs take that information and they can change the formulations of their grout to match that level of variability. So what it means is, if you can only achieve 90% homogeneity, so the probability of you finding a bunch of these highly radioactive particles in one location is too high, they dilute the system, or they add more grout. So less waste. So you basically need more casks to process the same volume of waste, because instead of, a liter of waste per 10 liters of grout, it might be half a liter of waste per 10 liters of grout, because of you not knowing what that concentration is. So, the mixing in the nuclear waste industry is a very interesting subject. And if there's anybody on the line who knows how fun pulse jet mixing is and the history of all that, this has been a very common question. But the stirred tank is much better than a pulse jet mixer, so at least we can measure these things. It's homogeneous, it's steady state. You can make measurements, and that's good. So we can make a decision from this type of data. Like, it does tell us what's going on. So when you do so I left out the discharge tests here, but you can really see what happens. We get about 85% of the volume out homogeneously, and the last 15% represents a heel. And so we then ask the customer, is that okay, or how can you deal with that? And they say, yeah, sure. I mean, that's the heel. So then we just add waste back on top of that, and then you just have to keep processing it, knowing that you're only going to be able to discharge 85% of that waste from the volume. So, you kind of make a decision in an iterative effect. So we tell our customer what we can do, what we can't do, and we iterate, like, how about, can you try this, or what if we did this instead? And so it's very iterative, right? And in a general perspective, I mean, we kind of think of agitator design as kind of a three-pronged approach. You have tools, right? You can do hand calculations, you know, you get your analytical solution. You can do experiments, the other leg of the triangle, and you have CFD. So some combination of those three aspects is how you might arrive at a confident agitator design. I mean, I wouldn't say we use CFD alone to design an agitator. We would use CFD to kind of characterize aspects of what an agitator can do to a system and use that information as valid as it is in depending on the situation to kind of inform the customer what we think is possible or if there's any risks. We're looking for risks, I guess. It's risk mitigation at the end of the day. It's like where do we think risks are?
Great, thank you.
So that's a long-winded version of that answer, I think.
Yeah.
Oh, that's perfect. Thank you.
Yeah, thank you. I guess it was an excellent final statement that we, of course, still need experiments and numerical simulations. We can learn from both, and it's a kind of risk management to see what is the most reliable at the end. Not very satisfying, but anyway, I guess this is the truth. Yeah. Joelle, would you like to add something?
No, I think I would just like to thank Jason for his talk, and I think it's been really great to have the different aspects. So we ended up really with an industrial application and starting with more fundamental from Georgina and Cees. So I think we probably can wrap up because we did go over time, and there's probably some people that need to go. So I would really like to thank all the participants for having joined, and I'd like to, thank especially Georgina, Cees, and Jason for, preparing their talks and really getting it into together for this spotlight talk.
Yes, thank you so much. It was really very, very nice. And also thank you so much for the participants for the nice discussion. I mean, we didn't need the discussion at the end because the discussion was already
going.
presentation. Yeah. So very, very good. Thank you so much. I guess we can be really satisfied. And this also thank you again to Martin to set this up and to our representatives from the EFCE. I guess it's really a very, very nice format that we have here to come together in a very easy way to discuss. Yeah. Thank you so much. So,
okay, it's been a pleasure. Thank you all.
Thank you for having me.
Thank you, Antonio.
Thank you. Thank you, Jason. Thank you, Georgina. Thank you, Cees. Wonderful presentations. Bye-bye, Martin.
Thank you, Martin.
Thank you. Have a good afternoon. Bye-bye.
Bye-bye, everybody.
Thank you. Bye.